Slide 1, Everything School. Acids and bases in organic chemistry. Proton transfer, pKa, conjugate pairs, and reaction direction. The main question for this whole lesson is, where does H plus go? That is the question I want you to keep in your head from the beginning to the end of the video. Organic acid-base chemistry can look complicated because there are formulas, charges, curved arrows, and pKa values. But most beginner problems are really asking you to track a proton. So on this slide, do not worry about memorizing every detail yet. Just remember the goal, find where H plus starts, find where H plus goes, and use that to understand the acid, the base, the conjugate pairs, and the direction of the reaction. Slide 2, what this video will make clear. The goal is not memorizing random definitions. The goal is knowing what to do on exam questions. By the end, you should be able to identify the acid and the base, draw conjugate acid-base pairs, use pKa without guessing, predict the favored side, and draw the correct curved arrows. The most important sentence on this slide is at the bottom. Most problems are proton tracking problems. That means when you feel stuck, start simple. Ask which molecule loses H+, which molecule gains H+, what forms after that proton moves. If you can answer those questions, you are already doing the main part of acid-base chemistry. Slide 3. Why acids and bases matter in organic chemistry. They show up inside mechanisms, not only in pH questions. This is a big shift from general chemistry. In organic chemistry, protonation adds H+ to make a molecule more reactive. Deprotonation removes H+ to create a stronger nucleophile. Proton transfer can also change leaving groups. A bad leaving group can become a better leaving group after proton transfer. And reaction direction is usually predicted with pKa. So this topic is not just one small chapter. Acid-base thinking appears again and again in organic chemistry. If you understand this now, mechanisms later will feel much less random. Slide 4. Part 1. Core acid-base language. First, build the vocabulary that every later example depends on. This slide is a section divider, so the goal is to slow down and set up the foundation. Before we use pKa, before we predict direction, and before we draw curved arrows, we need the basic language. Terms like acid, base, conjugate acid, and conjugate base are not just vocabulary words. They are labels that tell you what happened in the reaction. So in this first part, focus on learning the words in a useful way, not just a memorized definition way. Slide 5. The big idea, proton transfer, a Bronsted Lowry acid-base reaction is mainly about moving H+. On this slide, the reaction is labeled with acid, base, base, and conjugate acid. The acid loses H+, the base gains H+. The products are the conjugate base and the conjugate acid. Use the quick test shown on the slide. If it loses H+, call it the acid. If it gains H+, call it the base. This is the beginner-friendly way to label almost every Bronsted Lowry acid-base reaction. The acid does not disappear. It becomes the conjugate base. The base does not disappear either. It becomes the conjugate acid. Slide 6. 3 acid-base models. Use the model that matches the question. The table gives 3 models: Arrhenius, Bronsted Lowry, and Lewis. An Arrhenius acid makes H+ in water, and an Arrhenius base makes OH- in water. That is mostly useful in general chemistry and aqueous solutions. A Bronsted Lowry acid donates H+, and a Bronsted Lowry base accepts H+. That is the most useful model for organic proton transfer and pKa. A Lewis acid accepts an electron pair, and a Lewis base donates an electron pair. That becomes very useful in mechanisms, electrophiles, and nucleophiles. For this beginner organic lesson, focus on Bronsted Lowry first, who gives H+ and who takes H+. Slide 7. Conjugate acid-base pairs. Conjugates differ by exactly 1 H+. This is the key rule for reading the table. HCl and Cl- differ by 1 H+, so they are a conjugate pair. CH 3 degrees Celsius OOH and CH 3 degrees Celsius OO- differ by 1 H+, so they are also a conjugate pair. NH4+ and NH3 differ by 1 H+. ROH and RO- differ by 1 H+. When you are asked to find a conjugate base, remove H+. When you are asked to find a conjugate acid, add H+. Do not change the whole molecule. Do not add random atoms. Just change the molecule by 1 proton and adjust the charge. Slide 8. General chemistry versus organic chemistry. Same topic, different focus. On the left, general chemistry focuses on pH and pOH, Ka, Kb buffers, titration curves, and mostly aqueous solutions. On the right, organic chemistry focuses on pKa and structure, conjugate base stability, curved arrows, mechanism steps, nucleophiles, and leaving groups. The important sentence at the bottom is, in organic chemistry, the structure usually tells you the acid-base behavior. That means you need to look at atoms, charges, resonance, and stability. Organic acid-base questions are often less about plugging into an equation and more about interpreting the structure. Slide 9. Part 2. pKa, strength and direction. This is the exam shortcut that makes acid-base problems much faster. This slide is another section divider. Now that the core vocabulary is in place, we can use pKa as a shortcut. pKa helps you compare acid strength. It also helps you predict whether products or reactants are favored. So in this part, the goal is to connect acid strength to numbers and then connect those numbers to reaction direction. If you learn this part well, many exam questions become much more systematic. Slide 10. pH, Ka, and pKa basics. pKa is usually the most useful number in organic acid-base questions. pH tells how acidic a solution is. Lower pH usually means more H3O+ in water. Ka is the acid dissociation constant. A larger Ka means the acid dissociates more. pKa is a log-scale version of Ka. The big memory rule is lower pKa equals stronger acid. This rule is one of the most important rules in the whole lesson. Bigger Ka means stronger acid, but lower pKa means stronger acid. So do not treat pKa like a normal strength number. For pKa, lower means stronger. Slide 11, the most important pKa rule. Reaction direction depends on the acid on each side. Equilibrium favors the side with the weaker acid, the acid with the higher pKa. The fast version is simple. Compare the acids only. The higher pKa acid is the weaker acid. The favored side contains the weaker acid. This is the step students often skip. They compare everything at once and get confused. Instead, after you draw both sides of the reaction, find the acid on the reactant side and the acid on the product side. Compare only those acids. The side with the higher pKa acid is the side that is usually favored. Slide 12. The pKa ladder students should know. You do not need every number perfectly. You need the rough order. Low pKa means stronger acid. High pKa means weaker acid. Strong mineral acids are very low, often below 0. H3O+ is about negative 1.7%. Carboxylic acids are around 4 to 5. Ammonium ions are around 9 to 11. Phenols are about 10. Water is 15.7%. Alcohols are about 16 to 18. Terminal alkynes are about 25. Amines are about 35 to 40. Alkanes are about 50. To use the latter, find the acid on the reactant side, find the acid on the product side, and the reaction favors the side with the higher pKa acid. Also notice the accuracy note. pKa values are approximate and can shift by solvent. Slide 13. Strong acid versus weak acid. Strong acids give up H+ more easily. On the left, stronger acids have lower pKa values, are more willing to donate H+, and form more stable conjugate bases. On the right, weaker acids have higher pKa values, are less willing to donate H+, and form less stable conjugate bases. The slide also says acid strength decreases as pKa increases. That is the pKa trend again. If pKa goes up, acid strength goes down. So when you see a lower pKa number, think stronger acid. When you see a higher pKa number, think weaker acid. Slide 14. Strong base versus weak base. Base strength is the flip side of conjugate acid strength. A strong base wants H+ strongly. It is usually less stable, and its conjugate acid has a high pKa. The example shown is NH2-. A weak base is less eager for H+. It is usually more stable, and its conjugate acid has a low pKa. The example shown is Cl-. The key sentence at the bottom is, stable conjugate bases are usually weak bases. That means if a base is already stable, it does not desperately need to grab H+. If it is unstable, it is much more eager to grab H+. Slide 15. Part 3. What makes an acid stronger? The answer is almost always what stabilizes the conjugate base. This section is about structure. Instead of only looking at pKa numbers, we are now asking why those numbers make sense. The main idea is that acid strength depends on what happens after the acid loses H+. If the conjugate base can handle the negative charge well, the acid is stronger. If the conjugate base cannot handle the negative charge well, the acid is weaker. So in this part, every factor is really a factor about conjugate base stability. Slide 16. Acid strength depends on conjugate base stability. A stronger acid forms a conjugate base that can handle the negative charge. The main exam logic is shown clearly. If a minus is stable, HA is more acidic. If A minus is unstable, HA is less acidic. Always ask, where does the negative charge go? The stability meter points to the key idea, more stable A minus means stronger HA. This is one of the best ways to think on an exam. Do not just ask whether a molecule has H. Ask what happens after that H+ leaves. If the leftover negative charge is stabilized, losing the proton is more favorable. Slide 17. Factor 1, electronegativity. Across a row, more electronegative atoms stabilize negative charge better. The slide shows the row trend. Carbon is less electronegative than nitrogen. Nitrogen is less electronegative than oxygen. And oxygen is less electronegative than fluorine. Why does that matter? A negative charge is more stable on a more electronegative atom. More stable conjugate base means stronger acid. This trend works best when comparing atoms in the same row. The example idea is that OH acids are usually more acidic than similar CH acids because O- can hold negative charge better than C-. Slide 18, Factor 2, atom size. Down a group, larger atoms spread out negative charge better. The slide shows the halides F-, Cl-, Br-, and I-. As you go down the group, charge spreads out more. A larger atom gives the negative charge more space, so the charge is less concentrated. That makes the conjugate base more stable. The important pattern is this. Across a row, electronegativity is usually the main idea. Down a group, atom size becomes very important. Larger atoms can spread out the negative charge, and that can make the conjugate base more stable. Slide 19. Factor 3, resonance. Resonance stabilizes a conjugate base by spreading out charge. The slide focuses on acetate. Acetate is stabilized because the negative charge is shared over 2 oxygens. That makes the conjugate base more stable, which is why acetic acid is much more acidic than ethanol. The 2 resonance drawings show the negative charge on one oxygen in one form and on the other oxygen in the other form. The key sentence is, resonance usually makes the original acid stronger because the conjugate base is more stable. In other words, resonance spreads out charge, and spreading out charge usually increases stability. Slide 20, Factor 4, inductive effects. Electron withdrawing groups can stabilize negative charge through sigma bonds. The slide says electron withdrawing groups pull electron density through bonds, stabilize nearby negative charge, and make the acid stronger. The chlorine shown is an example of an electron withdrawing group. It pulls electron density. The closer the electron withdrawing group is to the acidic area, the stronger the effect usually is. This matters when 2 acids look similar, but one has an electronegative atom nearby. That nearby electron withdrawing group can help stabilize the conjugate base, which makes the original acid stronger. Slide 21, Factor 5, hybridization. More S character holds electrons closer to the nucleus. The slide gives the hybridization trend for CH acidity. An sp carbon has 50% S character. An sp2 carbon has 33% S character. An sp3 carbon has 25% S character. More S character stabilizes a carbanion better. That is why terminal alkynes can be deprotonated by very strong bases. The key here is not that terminal alkynes are strong acids in general. They are still weak compared with many oxygen acids. But compared with typical CH bonds, an sp carbon can stabilize the negative charge better. Slide 22. Part 4. Predicting reactions. Now use the same 4-step method on real organic examples. This section is where the earlier rules become a tool. We have learned the language, acid, base, conjugate acid, and conjugate base. We have learned the pKa rule. Lower pKa means stronger acid, and reaction direction favors the weaker acid. We have learned why acids are stronger, conjugate base stability. Now we combine those ideas into a repeatable method. This is the part that should feel most useful for exam-style questions. Slide 23. How to predict acid-base reaction direction. Use this exact algorithm before doing anything fancy. Step 1. Identify the acid and base. The acid loses H+, and the base gains H+. Step 2. Draw the conjugates. Remove H+ from the acid and add H+ to the base. Step 3. Compare pKa values. Compare the acid on each side only. Step 4. Favor the weaker acid. The higher pKa acid is weaker, and that side is favored. This algorithm is meant to keep you from guessing. If you follow these 4 steps, most beginner acid-base direction problems become much more organized. Slide 24. Worked example 1, acetic acid plus hydroxide. This is the classic easy win for pKa comparison. Step 1 is identify. The acid is CH 3 degrees Celsius OOH. The base is OH-. The conjugate base is CH 3 degrees Celsius OO-. The conjugate acid is H2O. Step 2 is compare acids. The reactant acid is acetic acid with pKa about 4.8. The product acid is water with pKa about 15.7. Water is the weaker acid because it has the higher pKa. Products are favored because the product side has the weaker acid. This is exactly the pKa rule in action. Slide 25. Worked example 2, terminal alkyne plus sodium amide. A terminal alkyne needs a very strong base. What happens? NH2- removes the terminal alkyne H. The product is an acetylide ion. Acetylide ions are useful strong nucleophiles later. Now use the pKa comparison. The reactant acid is the terminal alkyne with pKa about 25%. The product acid is NH3 with pKa about 38. NH3 is weaker because it has the higher pKa. Products are favored. This is why NaNH2 is strong enough for terminal alkynes. Slide 26. Worked example 3, phenol plus hydroxide. Phenol is more acidic than a normal alcohol because its conjugate base has resonance. Why does phenol work? Phenoxide can spread negative charge into the aromatic ring. A normal alkoxide cannot stabilize the charge the same way. Phenol has a pKa of about 10. Now compare acids. The reactant acid is phenol, pKa about 10. The product acid is water, pKa about 15.7%. Water is weaker, so products are favored. The key idea is that resonance stabilization makes phenol more acidic than regular alcohols. Slide 27. Curved arrows for acid-base reactions. Arrows show electron movement, not proton movement. Arrow rule 1. Start at the base lone pair or negative charge. Arrow rule 2. Point to the acidic H that is being removed. Arrow rule 3. Move the H-A bond electrons back to A. The common mistake is listed at the bottom. Do not start a curved arrow from H+. Start arrows from electrons. This is extremely important for mechanism drawing. A curved arrow is not just showing where atoms go, it shows where electrons go. So always ask, where are the electrons starting? Slide 28. How acid-base steps appear in mechanisms. They often prepare a molecule for the next reaction step. Protonation adds H+ to a molecule. It can make an atom positive, make a carbonyl more electrophilic, or turn OH into H2O, a better leaving group. Deprotonation removes H+ from a molecule. It can make a neutral molecule charged, create a stronger nucleophile, or finish a mechanism by restoring neutrality. This slide is showing why acid-base chemistry matters beyond simple acid-base questions. Protonation and deprotonation are often setup steps or cleanup steps in a full reaction mechanism. Slide 29. Common mistakes students make. These are the fastest ways to lose marks on acid-base questions. Mistake 1. Thinking lower pKa means weaker acid. The fix is lower pKa equals stronger acid. Mistake 2. Starting curved arrows from H+. The fix is arrows start from electrons. Mistake 3, comparing bases instead of acids. The fix is compare the acid on each side. Mistake 4, ignoring resonance and charge stability. The fix is always check the conjugate base. If you avoid these 4 mistakes, your acid-base answers will already be much cleaner and more reliable. Slide 30. Practice pause. Try this before the answer reveal. The slide asks 4 questions. Which molecule is the acid? Which molecule is the base? What are the conjugate acid and conjugate base? Which side is favored? Pause the video here. Do not rush to the answer. Use the algorithm from earlier. First, identify who loses H+. Second, identify who gains H+. Third, draw the 2 conjugates. Fourth, compare the acid on each side using pKa. Then decide which side is favored. The next slide will reveal the labels and the pKa comparison. Slide 31. Answer, reveal. Use pKa to decide the favored side. The labels are acid, CH3OH, base, NH2-, conjugate base, CH3O-, conjugate acid, NH3. Now compare pKa values. The reactant acid is methanol, with pKa about 16. The product acid is ammonia, with pKa about 38. NH3 is the weaker acid because it has the higher pKa. Products are favored. The reaction is favored forward because it forms the weaker acid, NH3. This is a direct example of comparing the acid on each side. Slide 32. Final recap, acid-base algorithm. Use this before every organic acid-base question. Acid donates H+. Base accepts H+. Conjugate pairs differ by 1 H+. Lower pKa means stronger acid. Higher pKa means weaker acid. Reaction favors the side with the weaker acid. Acid strength depends on conjugate base stability. Curved arrows start from electrons. The one-sentence summary is, find the proton, compare pKa, favor the weaker acid. This is the main takeaway from the whole video. If you can apply this consistently, you can handle many beginner organic acid-base questions. Slide 33. Accuracy notes for the video. Use these when checking the final narration and examples. For pKa values, use approximate pKa values unless your course gives a specific table. pKa values can change depending on solvent and conditions. The rough order is what helps most beginner problems. The recommended source checks are your course textbook or Professor pKa table, University Organic Chemistry notes, OpenStax Chemistry for general acid-base foundations, and Chemistry Libre texts for organic acid-base examples. The script warning is important. Avoid saying pKa values are universal. Say about or approximately when using common values. Slide 34. Acids and bases made simple. From confused to clear, this is the end screen. The next video suggestion is reaction mechanisms or resonance structures, because both topics connect directly to acid-base chemistry. Resonance helps explain conjugate base stability, and mechanisms use protonation, deprotonation, and curved arrows all the time. If this video helped, the next best step is to practice with real acid-base examples. Label the acid, label the base, draw the conjugates, compare pKa, and choose the favored side. Subscribe to Everything School for more simple help with confusing classes.